In the winter of 1686, the last ship of a desperate French expedition was balanced on a single failure point. The vessel was La Belle, a small bark long, roughly 54 feet long, sitting alone in the shallow, violent waters of Matagorda Bay on the Texas coast. Her commander, the explorer La Salle, was away on an overland expedition trying to find the Mississippi River and a route to French help. The ship was low on water, the crew was dying of thirst and disease, and the hull was their last way out. When the norther hit, it brought gale-force winds that turned the shallow bay into a cauldron of chop and sediment. The mechanics were simple and brutal. The anchor began to skate, and the wind load on mast and rigging did the rest. La Belle was driven across the bay and shoved onto the sandy edge of the barrier coast. As the storm shifted, the hull was worked loose, battered, and pressed down into the soft bottom. She took on water and settled into the silt. The bay swallowed most of her, but not the story. On April 4th, 1687, Spanish searchers reached Matagorda Bay and salvaged what they could, guns, the anchor, and rigging, then left the rest behind. What remained was sealed in a tomb of anaerobic mud, hidden from sight for centuries. For 3 centuries, the location of La Belle lived in documented accounts and imperfect charts. Enough to narrow the bay, not enough to pinpoint a grave in shifting mud. Matagorda Bay is turbid, darker than coffee, with visibility measured in inches. You do not find a wreck here by sight. You find it by instrument, by the faint magnetic fingerprint iron leaves in the mud. In 1995, archaeologists from the Texas Historical Commission began a grid search with a magnetometer, an instrument designed to hunt invisible anomalies in the bay's magnetic field. The Earth generates a consistent, planetary-scale magnetic field. When a large mass of ferrous metal, an anchor, a cannon, a pile of muskets, sits on the seafloor, it distorts that field the way a stone ripples a stream. A magnetometer, towed behind the survey boat, detects those minute variances and turns them into a trace the team can follow, iron and iron alone. The survey team ran long, tedious lanes back and forth across the murky water. The data stream was flat until the sensor crossed one set of coordinates. Then the line jumped, hard, a clean, high-intensity spike, one of the strongest targets on the grid. Whatever lay below was not scattered scrap. It was a concentrated mass, the kind of iron signature you'd expect from ballast and weapons locked together in a 17th century wreck. Verification required a human descent into the bay. The divers dropped into water so thick their instruments had to be read by touch and light pressed to glass. This was not swimming, it was work in a brownout, measured in inches. At the bottom, 12 feet down, the diver began to probe the mud with hands and metal rods. The first confirmation was tactile. The diver's hand struck something hard and cold rising out of the clay. It was a cannon, but it was not iron, it was bronze. Bronze weathers differently from iron, and in the oxygen-poor mud, the metal felt remarkably well preserved beneath the diver's fingers. The diver ran his fingers along the barrel and felt distinct, ornate handles shaped like dolphins. Near the breech, his fingers traced a raised crest. When the cannon was later examined, the crest was identified as the coat of arms of the Count of Vermandois, who served as Admiral of France from 1669 to 1683. The evidence was overwhelming. This was La Belle, and later checks against French archival records helped seal the identification. The anomaly was the ship that carried the ambitions of the French Empire in North America. The discovery was a triumph, but it immediately introduced a severe engineering problem. The ship was intact, preserved by the mud, yet she lay in zero visibility water, encrusted with sediment, and loaded with fragile artifacts. Standard methods would force divers to work blind, excavating delicate timbers by touch, slow, dangerous, and scientifically costly. They had found the ship. Now they had to change the conditions around it. The salvage team faced a binary choice that would dictate the quality of the entire operation. They could excavate traditionally with divers, feeling for artifacts in the dark, sucking up mud with hoses, and risking the loss of context. Or they could eliminate the water entirely. That second choice was expensive and industrial, but it offered what no diver ever could, a clear line of sight. They chose it. The solution was a cofferdam. A cofferdam is a temporary watertight enclosure built within a body of water to allow the enclosed area to be pumped out, creating a dry work environment on the seabed. It is essentially a hole in the ocean. For the Belle project, the engineers did not build a simple box. They designed a massive, double-walled steel fortress around the wreck site. The construction began with steel sheet pilings. These are long, interlocking, corrugated steel sections driven vertically into the bay floor. The team used a vibratory hammer to drive these sheets 40 feet down into the sediment. This depth was critical. The sheets had to penetrate far below the layer of soft mud and bite into firmer clay beneath to anchor the structure against the lateral forces of the bay. The geometry of the wall was the primary defense against collapse. A single wall of steel holding back the entire Gulf of Mexico would likely buckle under the strain. To solve this, the engineers built two concentric walls. The inner wall surrounded the ship, and the outer wall surrounded the inner wall. The distance between them was 33 feet. That gap was not empty. Once the steel sheets were driven, the void between the walls was filled with sand, transforming the hollow steel skins into a massive gravity dam. The enemy here was hydrostatic pressure. Water exerts pressure that increases with depth, pushing inward against any submerged hollow object with crushing force. In a single-wall cofferdam, the steel must resist this force entirely on its own strength. By filling the 33-foot gap with sand, the engineers created a structure so heavy and thick that the inward push of the bay water could not move it. The sand transferred the load down to the seabed, locking the walls in place. Once the perimeter was sealed, the pumps were engaged. The dewatering phase was the moment of truth. Over a period of days, pumps removed almost 500,000 gallons of seawater from the central pit, about 1.9 million liters. As the water level dropped, the steel groaned and adjusted to the load, but the walls held. The result was surreal, a dry, sunken courtyard in the middle of the bay. The archaeologists could walk down a ramp and stand on the bottom without diving gear. The air was salty and damp, but it was air. The removal of the water revealed the challenge that had been hidden by the murk. The ship was there, but it was not sitting on the surface. It was buried deep within the gray clay. The hull timbers were soft, waterlogged, and held together by the very mud that concealed them. The cofferdam had solved the visibility problem, but it had introduced a new threat. Now that the water was gone, the supporting buoyancy was gone as well. The wreck was now exposed to the crushing weight of gravity, and the mud that encased it began to dry and crack. The moment the pumps exposed the seabed, the clock started running on a chemical time bomb. For 3 centuries, Belle's world had been sealed in dense gray clay, an airtight tomb that kept oxygen out and time suspended. That seal was the only reason wood, leather, and rope still existed here at all. In the oxygen-rich environment of the surface, bacteria and fungi consume organic material like wood, leather, and rope. They rot it until nothing remains. However, the deep sediment of Matagorda Bay is so compact that it blocks the intrusion of oxygen. Without oxygen, the bacteria that cause decay cannot survive. The mud seals the wreckage in a sterile stasis. A leather shoe dropped in 1686 can emerge astonishingly intact in 1996. But when the archaeologists removed the water and exposed the mud to the air, they invited the oxygen back in. The preservation spell was broken. The excavation had to be precise, but it also had to be fast. The team rigged scaffolding over the hull to allow excavators to work without standing on the fragile timbers. They used plastic trowels and gentle streams of water to wash away the clay. They were not just digging for treasure, they were dismantling a time capsule that contained a complete kit for building a French colony. The inventory was staggering. They found crates of muskets, boxes of trade beads, cooking pots, and tools. In total, the site yielded more than 1.6 million artifacts. But the value of these items was not just in their physical existence, it was in their specific location on the deck. This is the concept of provenience. In forensic salvage, an object loses half its scientific value if it is moved without record. Provenience is the 3-dimensional coordinate of an object relative to the ship structure. It tells the story of the moment of loss. A musket found in a crate means cargo. A musket found next to a skeleton means defense. Before a single bead was lifted, its position was mapped digitally. This rigor allowed the team to reconstruct the final chaotic hours of the ship. The most sobering discovery lay in the bow. Coiled on a large pile of anchor rope, the excavators found a complete human skeleton, and elsewhere, scattered remains that pointed to another lost crewman. The forensic analysis suggested this was a male, likely suffering from thirst or injury, who had curled up on the rope to rest or perhaps to die. The anaerobic mud had preserved him. He was a direct witness to the failure of the expedition. His presence turned the technical salvage into a recovery of war dead. As the weeks passed, the small artifacts were cataloged, wrapped, and moved to wet storage tanks to keep them from drying out. The interior of the ship was slowly emptied. The cargo was gone, the guns were gone, the crew was gone. What remained was the container itself. The hull of Belle lay exposed at the bottom of the Cofferdam, white oak, curved and beautiful, and structurally deceptive. The wood looked solid, but it was spongy and saturated. It was too large to lift by crane without risking a break under its own weight, and too valuable to leave behind. The archaeologists had saved the contents, but now they had to figure out how to save the package. To the eye, the hull still carried the elegant curves of a 17th century light frigate, almost like something that could be pumped, patched, and floated again. But on the dry seabed, it was a structural lie. After 300 years, the chemistry of the white oak had changed. Stiffness was gone, and water had become the real framework. Press a finger into the timber, and it felt solid. Try to lift it, and the illusion collapsed. Straps would cut, the hull would sag, and the shape would fail. The only way forward was to take the ship apart and later replace the water inside the wood with something that could hold it up. Try to lift it, and everything changed instantly. The salvage team calculated the risks of a unit lift. In a standard recovery, a cradle is built around the hull, and cranes lift the entire mass. But for the Belle, the calculations showed a catastrophic failure mode. The hull was heavy with waterlogged weight, yet it lacked the tensile strength to support itself. If they ran lifting straps under the keel, the straps would not lift the ship. They would slice through the softened wood like wire through cheese. If they tried to brace it, the hull would likely sag and snap under its own mass the moment it left the support of the mud. The decision was made to abandon the idea of a unit lift. To save the ship, they had to destroy its form. They chose the path of disassembly. Disassembly is the systematic process of reverse construction. Instead of fighting gravity to keep the ship together, the team decided to take it apart piece by piece, in the exact reverse order of how the French shipwrights had built it in the 1680s. This was not demolition, it was controlled reversal, an unbuilding with a map. The process began with the ceiling planking, the internal lining of the hold. Each plank was cleaned of the remaining mud and inspected. Because the iron nails had long since corroded away into black stains or hollow voids, many of the timbers were held in place only by gravity and the friction of swollen wood. Where trunnels, wooden tree nails were used, they were often soft enough to be pushed out or carefully drilled. Every single timber was treated as a unique piece of evidence. Before a piece moved, it was tagged in plastic, a unique alphanumeric code tied to a master database mapping its exact location, curvature, and neighbors. Lose the tag, and you didn't just lose a plank, you lost the only way to ever put the puzzle back together. The work was backbreaking and wet. Even in the dry Cofferdam, the timbers had to be kept constantly wet with hoses to prevent premature drying. The archaeologists worked in a muddy slurry, prying loose heavy ribs and massive keel sections. One by one, the components of the Belle were freed from the clay. The stem post, the stern post, the keel, and the hundreds of hull planks were lifted out of the pit. The ship was no longer a vessel, it was a collection of lumber. The 54-foot hull had been reduced to hundreds of individual dark, wet shapes loaded onto pallets. The recovery was a success in that the wood was out of the bay, but the threat level had not decreased. It had just shifted. The wood was stable only because it was saturated. Let that water evaporate, and surface tension would pull the weakened cells inward until the timbers shrank, cracked, and twisted. They had the pieces, but the material was programmed to fail in dry air. They needed to replace the water with something solid. The battle to save the Belle moved from the mud of the bay to a laboratory at Texas A&M University. The enemy was no longer the sea, but the water trapped inside the wood itself. The challenge was a matter of molecular physics. As water evaporates from a degraded wood cell, the surface tension of the receding liquid pulls the cell walls together. Multiply this force by millions of cells, and a massive timber will warp, shrink, and tear itself apart. To prevent this collapse, the conservationists needed to replace the water with a solid material that would support the cell walls from the inside. The agent of choice was polyethylene glycol, known as PEG. Dissolved in warmed water, PEG acts as a bulking agent. It migrates into degraded cells and replaces the liquid that once held them open. Later, under controlled cooling and drying, it solidifies and supports the structure from within. The drawback is concentration. Push it too high and the timbers can end up heavy, dark, and waxy, muting fine surface detail and tool marks. Years into the conservation, after long soaking treatments with PEG, the team chose a more radical finish. They would minimize further immersion and use freeze drying as the final stage to stabilize the ship's timbers. This required the construction of the largest freeze dryer built for conservation use in the hemisphere. The machine was a steel cylinder 40 feet long with an 8-foot internal diameter resembling a submarine. This final stage depended on one phase change, sublimation, the direct shift from solid to gas, skipping liquid entirely. First, the timbers were soaked in the PEG solution until they were saturated. Then they were placed inside the steel cylinder. The temperature was dropped until the water and wax mixture inside the wood froze solid. At this point, the wood was stable, but it was filled with ice. If the ice melted, the water would return to liquid form, surface tension would return, and the cells would collapse. The engineers then lowered the air pressure inside the chamber to a near vacuum. In this low-pressure environment, the physics of water changes. When the chamber was gently heated, the ice inside the wood did not melt into water. Instead, it vaporized directly into gas. The water molecules detached from the ice crystal lattice and flew off as vapor, which was then sucked away by the vacuum pumps. Because the water never returned to liquid, the most dangerous force never came back. The ice simply vanished, leaving the waxy PEG matrix behind to support the cellular structure. The process was slow and unforgiving. The machine ran continuously, removing moisture gram by gram. If the power failed or the vacuum seal broke, the ice could melt and the ship could be ruined. But the machine held. When the chamber was finally opened and the timbers were removed, the result was a triumph of chemical engineering. The wood was light, it was dry, it was the color of toast. The dimensions had held true. The tool marks from the French shipwrights in 1686 were crisp and visible. The PEG had done its job as a bulking agent, and the sublimation had removed the threat of collapse. The Belle was no longer a rotting wet sponge. It was stable lumber. The conservation stretched on for more than a decade, far longer than the excavation in the Cofferdam. When it finally ended, the ship was safe from decay but still in hundreds of pieces, scattered on pallets and shelves. The final challenge was not chemical, but geometrical. Take this exploded view of a frigate and reverse the entropy. Put it back together. Reconstructing Belle was not a calendar project. The excavation in the Cofferdam took months. The chemical stabilization stretched on for years. The final phase, the physical resurrection of the ship, began in a gallery at the Bullock, Texas State History Museum in late 2014, with the rebuilt hull completed for public display in 2015. The challenge was that the ship was no longer a structural unit. It was a collection of hundreds of individual timbers, cured and stable, but structurally independent. The freeze-drying process had saved the wood from cellular collapse, but it had not restored the mechanical strength required to bear loads. The white oak was now brittle and light. If the team simply nailed the planks back together as the French shipwrights had done, the hull would shatter under its own weight. The solution was to build a ship within the ship. The engineers designed a custom internal skeleton, a cradle of supports that would hold every timber in its precise original position without forcing the wood to carry the load. This armature acted as the invisible strength of the vessel. The reassembly was a slow, public performance of forensic accuracy. The team used the alphanumeric tags stapled to the timbers during the disassembly phase to identify the location of every rib and plank. They worked from the keel up, placing the heavy bottom timbers first, then rising to the turn of the bilge. It was a three-dimensional jigsaw puzzle where the pieces were 300 years old and warped by time. As the hull took shape, the gaps in the history became physical. The upper works of Belle, the masts, the rigging, and the high decks, had been destroyed before the mud could seal them in 1686. The reconstruction did not pretend those missing sections were still there. The museum let the surviving hull rise to its true height, and where the wood ended, the structure simply stopped. The absence defined the violence of the loss. The viewer could see exactly where preservation ended. Below that line, the ship endured, Above it, history had been torn away. The completion of the La Belle offered the final piece of evidence in a geopolitical tragedy. The loss of this small frigate was the checkmate move against the French expedition. When the ship dragged her anchor and settled into the mud, she took with her the colony's mobility, their supplies, and their link to France. Without the ship, the commander La Salle was forced into an overland gamble for help, a march that ended in mutiny and his murder by his own men. The colony at Fort St. Louis collapsed into starvation and disease, and the few survivors were eventually captured by the Spanish or absorbed by local tribes. The wreck of La Belle became the physical proof of why the French claim to Texas failed. Today, the ship stands in a climate-controlled glass case, dry and stable. The decision to reject the standard diver survey in favor of the massive Cofferdam and the decision to freeze-dry the hull rather than soak it in heavy wax resulted in one of the most significant archaeological recoveries in maritime history. The salvage operation began with a magnetic spike on a sensor in murky water. It ended with the ship standing in the center of the capital, miles from the sea, the lost frigate made present again, and the object whose disappearance helped redraw the map of North America.